Alright guys, today we're going to be going over some ASTAM material, some ASTAM content. Now a lot of this exam is similar to the fundamentals FAM exam in terms of the frequency and severity topics. So there's frequency and severity, so that's a lot of the short term. And then there is also more advanced like frequency and severity concepts, and then you'll add on more rate making concepts, and then you'll add on a few more nuances to Born-Ferguson as well as chain ladder. So all those make up ASTAM. So one of the main things in ASTAM is you need to have a good understanding of frequency and severity distributions. More importantly, how to actually combine multiple different distributions. So here we have like the four main ones. So x given lambda equals Poisson, lambda is gamma, so x follows negative binomial. So you'll see those four. And these four are actually very critical because they can actually help you solve questions very quickly. If you actually just know that, okay, this is x given lambda is Poisson, lambda is gamma, so I know x is negative binomial. If you can see that immediately, it's going to help you solve questions very quickly. The next thing is the entire idea of splices. Now you don't want to get the concept of splices and mixtures mixed up, because splices are an entirely different concept than mixtures. So splices refer to the fact that you have two different distribution functions during different intervals. So, and they don't necessarily have to add up to 1. So for example, from 0 to 5, you can have a Pareto, and then from the 5 to 10, right, if it's from 0 to 10, 5 to 10, you can have another Pareto, right? And so the weights of those don't necessarily actually have to add up to 1, right? And the way that you can typically solve splice questions is you'll see you can either do the summation equals to 1, right? The probability over the entire interval should be 1, so you can sum to 1. And if it's proportion, you can even try to calculate the exact probability at a specific interval or at like a specific point. So what I mean is, for example, if you have 5 to 10, right? If it's 5 to 10 and it's 1 to 5, you know that at 5, that probability should be the same, right? At 5, that probability should be the same. So you can set those equal to each other to find that unknown variable. So that's splices, some of the common things you can do for splices. Again, you can also just sum them to 1, see what the value of those variables are. Next is insurance payment is expected value of the loss minus the client payment. So this is typical, but one of the common tricks to this is you actually use the survival function. So integral of s of x, right, from d to infinity is the same as the expected value of the insurance payment. Right, so you want to know the survival shortcut to a lot of the questions. Some of the questions you can very easily solve if you just know the survival shortcut. Then we have the mean excess loss. Now this is very important as well, because typically you'll not just be dealing with the loss, but you would typically be dealing with some sort of deductible, and when you're dealing with that, you will be dealing with excess loss. Right? What is the remainder of the loss, right, that is passed to the deductible? So that is the excess loss. Exponential we know is memoryless. That is why it follows the same distribution as the regular loss, because these are the four different excess loss distributions from the original loss functions. Next, frequency and severity. Right? Frequency and severity. We know that the expected value of the aggregate payment is the expected value of the frequency of the loss times the frequency of the payment per loss, or you can shift it to the expected value of the number of payments times the expected value of the payment per payment. Okay, so those are two different versions that you can use. Next is the aggregate severity, variance of the aggregate severity. So that is this simple form here. Again, you can use either the expected value of the loss or the expected value of the number of payments, right? Frequency of loss or frequency of payment. And then if you use frequency of payment, you obviously have to do the frequency, or the payment per payment instead of payment per loss. So you just have to pick which one is easier for that question and then use that version. Right, but again, those two versions should get you to the same answer. Hazard function is the entire idea that given that this probability is beyond a certain point, what is the probability that it is exactly that? So what is the probability that x is exactly x, given that we know that it is at least x? So that is hazard function. Now we have entire frailty models based off of this as well. And you can actually simplify that by using MGF or moment generating functions. Right, so one of the key concepts here is the moment generating function we know is the expected value of ETX. Right? And then if you take the survival of x and you take that is equivalent to the moment generating function of lambda evaluated at negative a of x. Right? Capital A of x, so the integral of a of x. So this is one of the common formulas you should know when dealing with frailty models. There are four different ways to evaluate tail weight. And by tail weight, we are referring to what is the distribution of values, right? Or what is the shape of the distribution of values at the very tail of the distribution, so at the very end, very large values. First is the number of positive raw moments. The fewer the number of positive raw moments, the greater the tail weight. Next is ratio of survival function. So as x approaches infinity, if the ratio also approaches infinity, then the numerator has a heavier tail. Now this makes sense, right? This makes intuitive sense if you have a survival function, right? Survival function is what? X is greater than some value, right? So that as x approaches infinity, right? If the ratio approaches infinity, we know that the numerator is going to have a significantly greater value. Right? Significantly greater value. It's going to far outweigh the denom. So then we know that the numerator has a heavier tail. Next is hazard function. As x increases, if the hazard function decreases, distribution has a heavier tail. Right? So as x increases, if the hazard function decreases, distribution has a heavier tail. Mean excess loss. So if the mean excess loss function increases, as d increases, distribution has a heavy tail. Mean excess loss, again, refers to the concept of after a certain point, d, what is the distribution of losses? Right? What is the excess distribution of losses? Right? Not just the distribution of losses, but distribution of excess losses. Right? So x minus d. Right? So as d approaches, if that increases, we know that excess is incredibly large. If that excess is incredibly large, then the distribution has to have a heavy tail. Again, this is not comparative. It is absolute that it is a heavy tail. It is a heavy tail for 3 as well. And then 1 and 2 are actually comparative measures where you're trying to see if it's a heavier tail than the other distribution. Then we approach these generalized extreme value theorems as well. So the entire concept of this is, what are we trying to model? We are trying to model two things: block maxima, and excess loss. Right. Excess loss is values above a threshold. So all values above a certain d, right? All values above a certain point. Right? We're trying to model those. How can we model those using a distribution? So that's one. The second one is block maxima. So you're trying to model what is the maximum of a given random sample. Right? What is the maximum value of a given random sample? That itself follows some sort of distribution. What is that distribution? That's what we're trying to find. Now for the block maxima, we have this term that it's if we can find some sort of non-degenerate distribution function. Right? If we can find some sort of non-degenerate distribution function, where if we take the limit as n approaches to infinity, right, of f of cnx plus dn, raise it to the n, and we get some distribution function h of x. Right, we get some distribution function h of x. Then we can say that the distribution of x is in the maximum domain attraction of h. And if that's the case, then we know that the block maxima follows the generalized extreme value distribution, which is this right over here. Typically, what you used to do to prove this is you prove that, okay, if you take the limit as n approaches to infinity of n times the survival function of x evaluated at Cn x plus dn, that equals negative natural log of h of x, which is sometimes easier to prove than the other version with just the cumulative distribution function. And then we have three types: Gumbel, Fretchel, and Weibel. And then those correlate with those are associated with the excess loss distributions as well. So that's some things about exam ASTAM that I went over. If we go over a few, like one leak code question, is just a brute force solution, right? Brute force solution to number of contiguous subarrays where the sum of the subarray adds up to a given value k or a given integer k. The brute force solution to this. What is the brute force solution to this? Brute force solution is you can generate all different contiguous subarrays of length 1 to length the number of elements in the array. So all contiguous subarrays of length 1, all contiguous subarrays of length 2, etc. until you get to length n. Find the number that add up to k, and then you have your total number. So that's the brute force way. Just how do you go about doing it? One of the things you can learn from this is how we actually divided and conquered, and we broke it down into subcases on different lengths. So that is one thing to learn even from the brute force case. In general, for rate making, right, we want to develop and trend losses first. So developing and trending losses, the development of losses is what? Development of losses is all chain ladder and Borg-Hagen-Ferguson, all those metrics, all those techniques. Trending losses, right? Trending losses is you take midpoint of the historical period or the experience period, midpoint of the forecast period, and then you trend those losses. And you first develop them and then you trend them. So you're trending the developed losses to get to the ultimate losses, right? And that's your L over here. And then we know the parallelogram method, which is used to calculate the premium at the current rate level. What is the current rate level? Well, how do you get the premium at the current rate level? You multiply the premium times the on-level factor. How do you get the on-level factor? You calculate the overall rate, which is the current rate after you've gone through all of the rate changes, divided by the current rate, which is, depending on the calendar year, it's the weighted average of all of the rates. And where do the weights come from? Well, it's dependent upon how many policies were written at those time intervals, and you calculate that through the areas. So rate 1 was applied here. What's the area of this? How many policies is this area? Right, geometrically. Find that area, find this area, find this area. That's your weights. Those are your weights for the rates. Then you calculate the overall weighted average of those rates. That's your current rate. Overall rate over current rate, that is your on-level factor, right? That you use to multiply to the premium to get the premium to the current rate level. So this is a common question, seen it in SOA exams as well. So that's a bit of some content for ASTAM. I'll see you in the next video.